All right, so let's continue and let's talk about this thing called specific heat. So specific heat is the amount of energy needed to raise 1 gram of a substance by 1 degree centigrade. And you're probably thinking, hang on, didn't we just learn that? Wasn't that a calorie? The calorie refers to water only. The calorie is the specific heat of water. Specific heat is something that we can apply to any substance. So we can take any substance and measure how much energy we need to raise 1 gram of it by 1 degree centigrade. Now, if something has a higher specific heat, it's going to require more energy input to make it warm up. You've experienced this undoubtedly either by walking on sand at the beach or by walking on white and then black pavement in the summer. The black pavement is going to heat up really fast and the sand is going to heat up really fast. They have a lower specific heat because it takes less heat to increase their temperature. Water has a freakishly high specific heat. Like, it's so high, which is good for life on Earth. Thank goodness water has such a high specific heat. Those water molecules, they love their hydrogen bonds. They do not want to let go of each other. Okay. When we talk about specific heat, we use units of joule over gram degree Celsius. So a joule is just another unit of energy, and it's about like a quarter of a calorie-ish. So 1 calorie is 4.184 joules. And so when we look at specific heats and compare them with different things, water in its liquid form has a specific heat of 4.184. Now notice this is joules per gram degree centigrade. Both gram and degree centigrade are on the denominator of the fraction. So if we were going to write it, we could write it like this, gram degree centigrade. Okay, we would write it like that. Okay. Notice that iron has a specific heat of 0.452. It's like, it's not 1/10 of water, but it's way low, which is why your cast iron pan heats up so much faster than the water in it. You have to put a lot more heat in the water to get it to heat up. Aluminum, we talked about aluminum, and I said, I don't know, it seems like it's like would be a metalloid because it doesn't conduct heat as well. It just has a higher specific heat. You have to put a lot more energy into the aluminum, which is in fact a metal, to get it to heat up. So that's what I was talking about when I said some are better conductors of heat than others, because they have different specific heats depending on, well, lots of things that we're not going to go into this on this class. Anyway, just know they're all different. Okay. All right. Now, you know that adding or removing heat can cause a change in the state of matter. So if you heat up water, it can change into a vapor, right? If you remove heat, it can turn into ice. Heat, remember, is thermal energy. It is a form of kinetic energy because it is a measurement of the movement of the atoms and molecules. They literally bounce on things and cause friction, which causes heat. So faster movement means more heat. And when heat moves from one area to another, the speed of those movements changes. So if you have, say, a hot area and a cold area, this area has high heat energy, this has low heat energy. Once they touch each other, the heat starts to move from the area of high energy into the area of low energy, just like a ball rolls downhill from an area of high gravitational potential energy to an area of low gravitational potential energy. And that heat is going to continue to transfer until both areas are at the same temperature, meaning they are at thermal equilibrium. Okay, so the heat energy has moved from high energy to low, or from hot to cool. All right. A chemical reaction is a rearrangement of atoms and molecules, and a lot of chemical reactions produce heat. In fact, all of them produce some heat. Some produce a lot of heat. For example, burning octane. Octane is the main thing in gasoline that burns. And when you burn octane by combining it with oxygen, it produces carbon dioxide and water and a ton of energy. So this is octane. Its chemical symbol is C8H18. So it's 8 carbon atoms surrounded by 18 hydrogen atoms. We need 2 molecules of that, so that's what that 2 is for. We combine that with 25 molecules of oxygen, and then we're going to do some rearrangement. We're going to take these carbons, combine them with some of these oxygens, and those make 16 molecules of CO2. So we had 16 carbons, right? We had 8 carbons in each molecule and 2 molecules, so that's 16. So we get 16 molecules of carbon dioxide. Then we take the 18 atoms of hydrogen, combine them with the rest of the oxygen, and we get, oops, that's not supposed to be 8. Oh, no, that's 18. 18 molecules of water. See, I don't trust my math, but we have 36 hydrogens because we have 18 times 2. All right, so we have 36 hydrogens over here. Got to make sure we're balanced. All right. Now, this is what we call an exothermic reaction because this reaction also produces a lot of heat. Okay, so there is more energy here in these molecules than there is in these molecules. So the energy has been transformed into these molecules and heat. Got it? All right. So an exothermic process or reaction is anything that releases heat. So when you burn wood or octane, it causes a chemical change in the wood and releases heat. And what to remember is that the products, what you end up with at the end of the chemical reaction, when the chemical reaction is all done, those products have less energy than the reactants had. So some of the energy has been lost to the environment as heat. Freezing water is an exothermic process, and this is confusing. Like there's just no way to get around it. This is confusing. Because if you think about it, when you freeze water, the water gets cold. So what you're doing is you're removing the heat from the water and putting the heat outside of the water, out of the environment. Okay? So it's exothermic. The water itself gets colder. The environment around the water gets warmer because the water got colder. Because the heat moved out of the water. Now you're thinking, but hang on, my freezer is cold. That's why it makes ice. Yes, and the fact that the heat in the water has to be removed is the reason that the motor keeps turning on to keep your freezer cold. See it? Because the water releases heat into the freezer, and then that heat has to be removed from the freezer. Get it? Okay. Endothermic. An endothermic reaction or process absorbs heat. So if you think about a cold pack, like those little, I know it's winter, it's not time to think about cold packs, but if you think about, those things and you like smush them and then they get really cold and you can put it on like on an injury. The products, the cold pack, has more energy inside it than the ingredients of the cold pack. And now you're thinking, but it's cold. Isn't this the same as ice? And the answer is no. It's not the same as making ice because the cold pack has created new chemical bonds that have stored that energy. And it has removed the heat from the outside and stored it inside in a different form. And so that's why it's cold. Hopefully that made sense. I'm going to post some videos of exothermic and endothermic reactions. Just remember that heat is not the only form of energy. Okay, so we can break chemical bonds to release energy, but when we make chemical bonds, we store energy and we absorb energy. So we're absorbing energy from the outside environment and creating something that's not hot. We could have added heat as energy, that's a form of energy, but then we created chemical bonds instead of heat. We transformed the energy into a different form. Got it? Hopefully that helps. If not, just memorize these, please. Okay. So this is what happens in a cold pack. You've got ammonium nitrate. Yes, by the way, it is the same thing. That is a fertilizer and can be used in a bomb. Yeah, it's very reactive. Not with water, though. In the cold pack, you just mix it with water. And the ammonium nitrate, hang on, ammonium nitrate, that's 2 polyatomic ions, isn't it? Isn't ammonium and nitrate both ions? Why, yes, they are. Thank you for remembering. That was very nice of you. Oh, I don't want the laser pointer. Hang on, I want the pen. Come back. I want the pen. And I want the pen to be blue. Okay. Yeah. So it is NH4NO3. Yeah, that's ammonium nitrate. It's sitting in these little white pellets, and when you mix it with water, not O2, H2O, then it is going to, these two are going to divide into their ionic forms. And now you're thinking, but aren't we breaking a chemical bond? We are. And so this one is a little weird. What we end up with, I'm going to put this down here. What we end up with is NH4 minus plus NO3, wait, NH4 plus, sorry, not minus, plus, that's a plus. That's an H. Really good penmanship. Plus H2O. And you remember, when we mix an ionic solid into water, the ions dissociate and get surrounded by water. Well, that creates bonds between the water, I'm just going to do a W for water, and between the nitrate. This is the no, that's the nitrate, and that's the ammonium. Okay, so just like the dissociation of sodium chloride, ammonium nitrate does the same thing. These bonds, why did I use yellow? That was a bad choice. Okay, is orange better? These bonds, they're kind of like hydrogen bonds, and they absorb a lot of energy when they form. Yeah. So we took the energy in the form of heat and transformed it into chemical bonds. Ta-da! How's that? Yeah? Help? Okay. Hopefully that helped. All right, now, changes in state of matter. Adding heat causes a solid to melt into a liquid. So the transformation from solid to liquid is melting. From liquid to gas is either called evaporation or vaporization, or it evaporates or vaporizes. Those are the words I was looking for. Removing heat causes gas to condense. Condensation is the process of moving from gas to liquid form. Liquid to solid is freezing. Okay. Now, in some circumstances, these terms, by the way, you need to know all of these and these other two, which are wackadoodle. Sublimate is when a solid bypasses the liquid, goes straight onto gas. Yeah. And deposition, which is where a gas may turn directly into a solid without going through the liquid state. Both happen when temperature and or pressure are very high relative to the freezing or melting point of the thing, or the evaporation point of the thing. So dry ice. Dry ice is frozen carbon dioxide. And carbon dioxide at any normal temperature is a gas. It has to be really, really, really cold to be frozen. When you put it at room temperature, the temperature is so different between the dry ice and the outside environment that the carbon dioxide goes straight from solid to vapor. It doesn't turn into a liquid. And so that's what's happening here. Here's the dry ice, and you can see there's just vapor coming off of it. Okay. Do not touch dry ice with your bare hands. It will damage your tissues. Yes, please. It'll kill your skin. Yeah, bad. Okay. So this is just a graphic showing all of those terms and where the heat is going. Okay. Now remember, adding and subtracting heat is part of endothermy and exothermy, right? But remember that when we're going this way, these are endothermic because we are putting more heat into the water. In this case, this is ice and liquid water and water vapor. Okay, so the heat is going from the environment into, in this case, the water. Going this way, the heat is going from the liquid or the gas or the liquid into the environment. So there's less heat in this thing than this thing. Hopefully that made sense. Hopefully all of that made sense. Okay, that's the end of the lecture. Take care.